We ran through a bunch of waves derived from the cloud temperature and humidity and reanalysis data for various other fields. Maybe you didn't notice the similarities in nearly all of the waves in many vertical structures. So we'll highlight a few of those and then list the specific features that are self-similar in all the waves, and they also happen to be similar at mesoscale convective systems to convections at larger scale and even planetary scale. So if you look at the specific humidity associated with the Kelvin wave we derived, for example, the lag zero here is when the signal maximizes at the chosen location. So ahead of that we had moisture building up with cumulus congestus processes and feeding the troposphere, and then convection happens, and then there are complicated processes behind. As we had said before, these lead lag relations are very critical for the selection of the propagation directions in the waves, depending on which wave you are looking at. For example, in the westward propagating inertial gravity waves, we look at the heating structure here. So there is heating perturbations of heating and negative, so cooling, not necessarily, well, it's a negative anomaly of heating, positive anomaly of heating. So you can see the subtle lead lag relations, and these happened in all of the waves that are getting forced. And then there are these vertical velocity structures that can be inferred from vertical structures. So mixed Rossby gravity wave meridional wind at Mahuro again shows these vertical structures, what's happening in the lower levels and what's happening in the upper levels, and so on. If we summarize the similarities in all these vertical structures, we can say while their horizontal scales and propagation characteristics differ widely, their vertical structures display a remarkable level of self-similarity regardless of the wave considered. Okay, so we looked at eastward and westward propagating waves with various different phase speeds, wavelengths, meridional structures, and so on. So they all differ, but when we look at vertical structures, with the exception of the equatorial Rossby waves, all of the convectively coupled equatorial waves, as well as the MJOs that we have looked at and the equatorial waves, not just convectively coupled equatorial waves, are characterized by the following features: anomalously warm lower tropospheric temperatures ahead of the deepest convection, as inferred from the large-scale upward vertical motion and cloud top temperature minimum from surface to 500 hectopascals, so mid-troposphere, transitioning to cold perturbations just prior to and during the TB minimum. Okay, so there are vertical processes that are moistening the atmosphere. There is expansion, radiative cooling, and so on, and the TB minimum happens just prior to and during the TB. Cold perturbations happen just prior to and during the TB minimum. Anomalously warm upper tropospheric temperatures in the layer from 500 to 150 hectopascal, so mid-troposphere to the let's say lower stratosphere, peaking at around 250 hectopascal either just prior to or coincident with the deepest convection. So deepest convection is setting the response above, including the waves and the vertical structures. So you can go back and look at all these figures we flipped through with these things in mind. Thirdly, a change in the direction of vertical tilt or the elbow in the temperature and wind fields at 250 to 300 hectopascal such that perturbations ascend with time below this 250-300 hectopascal level, and they descend above that level. So We will see what we mean by that in a schematic soon. Convergence and moistening of the lowermost layers ahead of the deepest convection, followed by a rapid lofting of moisture throughout the entire troposphere just before the onset of deep convection. So this is where the whole moisture mode ideas come from. As we said, the debate is still about whether it can be lifted from the surface and whether the surface fluxes are important, frictional convergence, or there are tropospheric processes that are able to do this. Quickly evolving into moist over dry signal during and immediately following a convective peak, and a separate cold dry signal in the shallowest layers near the surface during the time of downdrafts. Okay, so this is nicely put together here. The hierarchy of cloudiness, temperature, and humidity within the convectively coupled equatorial waves, valid from mesoscale convective systems to MJO scales, which are the planetary scales. And the similarity is that these series of processes happen as the wave is moving from west to east. And you can see ahead there is the inversion. So there is strong convection and there is inversion around the strong convection. So subsidence of dry air is happening and into the below the 0 degree C line, freezing level, and there is trade inversion within which you begin to build cumulus, shallow cumulus, which then turn into congestus cloudiness, which begins to take moisture up to the beyond the freezing level. And then you have deep convection, which is being fed by the warm moist air that has now already existing ahead of the deep convection. So that warm moist air going into the upper level is obviously feeding the deep convection, and you have cold cloud top temperatures affecting even the tropopause. Obviously we get the tallest clouds and the coldest temperatures up here, and then you form the stratiform cloudiness, and there is stratiform rain falling from above into the dry cold regions, which then evaporate the stratiform precipitation. Okay, so behind that again you have similar inversion and shallow cumulus happening and subsidence over the freezing line above the freezing line. Okay, so there are nice papers written by many people on this, including the details by Brian Mapes and Johnson, Straub and Kelaris, Kuider and Maeda, and so on and so forth. So if you remember the skeleton theory of the MJO, took these multiple scales and tried to use them as the main feature of MJO theory in their case. And this is a nice example of such a multi-scale process that is happening at different scales. Obviously here lead lag also correspond to the spatial scales. So here the lag height regression of specific humidity versus rain rate from Toga core, tropical ocean global atmosphere experiment, the core observation period, coupled ocean atmospheric research experiment, had outer sounding array. The data are progressively regridded to coarser time intervals of 6 hour, 1 day, 4 days. So 6 hour, 1 a daily mean and 4-day mean. And here the original unfiltered 6 hourly data are used with a very wide lag window. So this is the much larger scale, short scale, daily scale, and multi-day scale here. And you can see that the relative humidity or specific humidity here have very similar structures in terms of the lead lag. So the moistening ahead and the stratiform and the vertical structures behind are all kind of similar at these multiple scales. I think this is referred to as sorry, let me just find this key word. It's called the stretched building block hypothesis, which states that the relative abundance of shallow, deep, and stratiform cloudiness is modulated by the large-scale environment, whereby life cycles of individual mesoscale convective systems are aliased onto longer time scales through linear superposition. So that explains the self-similarity at the various scales, at least in terms of consistency check. It doesn't give us fundamental theoretical understanding, but from observations it's clear that these are the self-similar processes happening at multiple scales from MCS to planetary scales, which is needed, of course, to explain the rapid deep convection condensational heating and the radiative cooling that's happening with the clouds stretched out at the planetary scales, which we had invoked before when we were discussing MJO theories. Okay, so it's nice to revisit this in the convectively coupled equatorial waves and the processes that are seen in all of these waves in the vertical structure, despite their very dissimilar horizontal structures. Okay.